All right, good morning. I'm going to try to work without the mic, but if you're having trouble hearing me, let me know and I'll either use the mic or yell more or something. So I'm going to talk a little bit this morning about sort of taking some of the things I talked about yesterday and how we actually put that together into a forecast. And in the 45 minutes I have this morning, I can't teach you all to be trajectory analysts, but hopefully I'm just trying to give you a little bit of a taste of what it is we do and how we do it. And then I'll show you the tools we have publicly available that Jordan mentioned. A real quick demo of those. So just as an example, this is a big one. In the case of Deepwater Horizon, really through April 21st through August 23rd, so 3 months there. We put out a forecast every single day. We actually were doing 2 a day for the first week or 2, and that was just crazy, so we worked down to 1 a day. For a 24, 48, and 72-hour period. So this was really a focus on so the responders could have some idea what to expect over the next couple days as they kept kind of moving forward in their planning cycle. So the basic steps, and this is what we do every time, is first we initialize oil location. And we do that by looking at all the observations that are available to us. And in the case of Deepwater Horizon, there was a lot. There was a satellite analysis. There were an enormous number of overflights going out there. There were ships out there telling us what they saw. So we try to just put all that together and get a sense of where we think the oil is now. And we can initialize from that. And then we put that together with the winds. As I talked about yesterday, we need to know the winds and the surface currents. And that we use our model, which I'll show you later, to kind of put all that together, and that moves the oil forward in time. And then we create a kind of our final forecast product, which a lot of people saw. These were all over the place, which can then be used in the incident command. So the basic kind of steps to doing this successfully. The first question is to understand what questions are we trying to answer. And our forecasts and our trajectory analysis are really usually focused on the operational aspects of response. So the questions we're trying to answer are, where's the oil going to be in the next couple of days? What might it look like when you get there? Are we expecting to see tar balls washing up on the beach, or thick mats of oil, or just a thin sheen? But so we have to, and the real point of this is so responders can do something about it. So we really focus on the information that might actually be actionable. Oh, okay, we're going to want to get ready to protect this marsh. We're going to want to be able to send skimmers out to this location tomorrow. Those kinds of basic operational questions that we're trying to inform. So to do this, the first thing we do is visualize the time and length scale of the challenge. What kind of problem are we dealing with? Is this a 1-day issue, or is this a 3-month issue? Is this going to be an issue over in a kind of range of a few miles, or hundreds of miles, tens of miles? And so yesterday when I was talking about the different kinds of currents and what their length and time scales are, it was exactly for this, so that when we first get an event and we know something got spilled in a particular place, or maybe something is a potential of being spilled, we immediately start to think in terms of time and length scales. What kind of is the scale of the problem? And once we've done that, we can try to pick the correct tools. So just again, as a little example, in Deepwater Horizon, we mentioned here multiple forecast models. So this was a really large-scale spill that covered a good chunk of the northern Gulf of Mexico. So we had available to us a number of models that are designed to model the entire Gulf of Mexico. And in this case, those were really very useful. But in a small-scale spill up here near Mobile Bay, those models of the Gulf of Mexico are worthless. We need the details in a small location. So once we've kind of scaled the problem, we have a better idea what tools we want to use and what's available to us. And then we got to find the data. So we go out there and we look for, like for the winds, there's a lot of in situ wind buoys on the NDBC stations, and we can look at what the winds have been doing. They don't give us a forecast, but they let us know what's been going on so far. We look for HF radar if that's available. There's a few places in the world where there's actually current meters in the water that are reporting real time, and that's really great when we have that. So we just try to find everything available that might inform us. And then a really big one is understanding the uncertainties involved. So especially when we work with a weather forecast, we will talk directly to the forecaster and not just get their best estimate for what the wind is going to be doing tomorrow, but some assessment from them about what they think the uncertainties are in that. And often there's some things they're very certain about, and other times they're not sure. A lot of the times it's actually timing that's what's least certain. It's like, okay, there's going to be a front moving through, and there's going to be a big shift in the wind direction when that happens. We think it's going to happen somewhere around noon, but maybe it won't happen until 3 in the afternoon. Maybe it won't happen, or it'll come in a little earlier. And that can often make a lot of difference as to the timing of that activity, especially as it relates to, say, the timing of the tides. So if you have an onshore wind that's going to kick in maybe at noon, but maybe not until 3 in the afternoon, maybe where the oil is going to be when that onshore wind kicks in can make a lot of difference. So we always want to understand for any of our data inputs, how uncertain is it? Not just what its best estimate is, but how uncertain it is. And then the final step, once you do a model, is we don't provide model output. What we provide is a forecast. And so we try to craft a product, whether it's a map or a written analysis, that is designed for the audience that we're speaking to and answers the questions they want. So one of our input data here are meteorological models. Primarily we work with the National Weather Service because we cover the U.S. and they're the most folks best to go to there. The forecasters, the NOAA forecasters in the offices work with these models, but again, like us, they don't actually just give us model output. They're usually looking at multiple models, and they'll have experience in their region and know that under these conditions in this region, this model tends to perform better, and this model doesn't perform as well. And they kind of put all that together to produce a final forecast. So we work with them to try to understand what they've done and what works best. And then often we will work with them to get a site-specific forecast. So they may, up on the web, you can go and just see what the coastal waters forecast is for mariners in a region. But we might want to know some detail about what's going on exactly at the spot we're in, and they can be very helpful in doing that. In a larger scale spill, we can spin up the Weather Service so that they'll be producing a forecast specifically for the spill response that they deliver directly to the command post. In smaller scale ones, we work, they do that through us. And then another one of our big inputs, as I mentioned, is ocean current models. So there's getting to be more and more of these models running in a nowcast forecast mode so that they're available to us to use whenever we want. They kind of fall into a couple of categories. The real operational ones are run primarily by the U.S. Navy and by NOAA. The Navy mostly runs pretty large-scale models, global scale or sort of Gulf of Mexico scale stuff. Which doesn't give you the kind of detail we might need closer to shore, but for large-scale spills, it's very helpful, and it still gives us a general idea of what's going on with the currents and whatnot. Like I talked yesterday a little bit about the California current system and how sometimes the Davidson current pops up and goes the other direction. The scale of the models that the Navy runs will resolve that and kind of let you know whether the general trend is north or south along the coast, even if they don't catch the details right into shore. So that can be very helpful. The other category is academic models. So a lot of universities will run models. For the most part, academic models are designed to try to understand something about the science of oceanography rather than to provide an operational forecast. They're trying to say, what is the impact of the Mississippi River's freshwater inflow on the circulation in this area? And they're trying to answer that question, and they use a model to do that. But a sort of nice side effect of that is that they are in fact forecasting the currents in that region, and we can try to make use of that when we make it available. And we've been working with a lot of different academic groups to try to, as long as they've got these models running, make the data available. Part of the trick, though, is those models are running when they happen to be running because they're doing a study or they actually have funding in place to do it. And usually their funding comes in these sort of short chunks. They get enough money to kind of get the things set up and maybe running for a year, and then without continued funding, it just goes away. But if they're there, we'll use them. And then there's response models. And there are a lot of places where there aren't already nice, accurate current models running in a place. And so we have our in-house tools that we've developed that we can spin up very quickly. We can go to just about anywhere in the world and within a couple of hours have a very simple hydrodynamic model that can help us forecast where currents are going. In that case, we usually need to have a pretty good idea what we're expecting them to do, and the model helps us work out the details rather than the broad physics of it. So if it's a tidally dominated area, that's an area we can do pretty well. If we've got a tide station nearby, we'll know what the tidal currents are doing in one point, and we use the model to help kind of extrapolate that to, say, the rest of the bay. Or as I mentioned, with something like the California current system, we'll look at what's going on with the HF radar, what's going on in some of the Navy and NOAA global scale models. And that'll say the California current is, going south at this point in this region, and we use our model to figure out exactly how it's getting steered by the local topography, the details. So the other model we use is the ADIOS weathering model. And I'm going to just skip through this quick because I'm going to demo it later. But in short, the things Jordan talked about yesterday about weathering, what goes on with evaporation and with dispersion, is we're putting all this, make an equation out of all of it, and then we run through it for a particular type of oil, particular set of conditions. We sort of try to make a forecast about how that oil is going to change. And then for our trajectory model, where the oil is going to go part, we use GNOME, which we've developed in-house. And again, what it does is it takes the stuff I talked about yesterday and turns it into computer code, so that, we did a quick calculation and saying, all right, if the wind is 10 knots towards shore, the oil is going to take, this long to reach shore with the 3% rule. And that's pretty easy when the wind is steady and in one direction. But if you start thinking about how in a forecast the wind's going to be changing direction, it's going to be changing speed, there's a lot of arithmetic to do there. So we just let the computer do that for us. And then we also combine it with, all right, the tidal currents are also moving it at the same time. And so this all gets pushed together. And the way it works is that we actually sort of pretend that the oil is a bunch of individual particles, and each of these particles then behaves individually and moves. And that's how we capture the spreading and the different motion of the oil. And in general, at the end of the day, where the particles are close together, it's where we're expecting higher concentrations of oil. Where they're further apart, we're expecting lower concentrations of oil. A lot of the details, the surface wind effects, what's going on with waves and language circulation and all that kind of gets pushed into one wind drift factor. And so I talked about the 3% rule. That's our starting point. But it turns out that observationally we've noticed that even if there's a steady wind at a fairly steady speed and direction, the oil tends to spread out in the windward direction. And it also collects a little bit more kind of on the front, and we get this sort of common effect. So when in the model, what we actually do is start at, say, 3%, but then have a little random variation and maybe move some particles a little bit faster than that and some particles a little bit slower. So we're modeling the spread as well. Within GNOME itself, we have some very simple weathering algorithms. We don't get into all the complex math. We use ADIOS for that. But it will at least just sort of make gasoline go away in a matter of a day or less, and heavy fuel oil will stick around. So you can kind of just scale what's going on for weathering. And it does actually have a 3D capability. We haven't used that a whole lot, and we're working on extending its capabilities. But if you have a deep subsurface spill like we did in Deepwater Horizon, or actually you want to model some other chemical that doesn't float, we do have a 3D capability. So for the general public, we have created what we call location files for GNOME. And this is, we've taken the model for a specific location and tried to capture what goes on in that region with the circulation and pre-developed currents and current patterns so that you can then kind of go through a particular region and answer a few simple questions, and you get a model for how oil might behave in that region. The key is that what we generally capture is sort of the climatology, what generally happens in that region most of the time. It's not necessarily what's happening out there today. And so it's important if you go and play with these that they're very helpful for intuition building. They're great for creating scenarios for drills. We use it in education in schools. And it gives you a realistic idea of how an oil spill might behave, but it doesn't. It's very hard to then say this is how an oil spill is going to behave tomorrow. And so when we're doing a response, we might, if it happens in one of the places we have location files, we may start with the location file, but then we're going to go in and re-examine all the details in there and determine whether that's appropriate for what's going on right now. So on our website, and this link is elsewhere also, GNOME itself and all the various location files are available. So here's a quick rundown of all the ones we have. In California, we have Santa Barbara Channel and San Diego Bay, a couple of them up in Alaska, Columbia River, a bunch on the East Coast. We sort of have produced them. They take a lot of work to put together, so it's kind of, we've been working with the Coast Guard over the years and kind of prioritizing areas that are both sort of useful for planning, and there's local interests, and there's all those reasons, and also something that we feel like we can capture in this simple location file. Places like one reason we don't have San Francisco Bay is because it's really complex and hard to kind of package up in a quick little easy to use model. So I just want to talk a little bit about how we kind of go through the process of starting with observations, overflights, and we put that together, initializing GNOME and run GNOME, and we also are grabbing, this for instance is the output from one of the circulation models for the Gulf of Mexico, showing the loop current here, and this is the region where the Deepwater Horizon spill was. So we put these observations and the models together and stick it into the thing, and then at some point we've got to kind of get to this end result of a final product. And one of the key parts of that, again, is the uncertainty analysis. So when we put together a forecast, we want to make sure not to just give our best estimate for what we think is going to happen, but scale the uncertainty around that. I think I have a... right, and so what are some of the sources of the uncertainty we can deal with in this? The observations themselves are pretty uncertain. We had this great satellite analysis that NESDIS was doing. They were looking at a bunch of different sensors. Judd talked about that a little bit briefly yesterday. But it's really not complete. There's places where the satellite doesn't go. There's places where there's cloud cover, so some of the sensors aren't able to see anything. And also, there's always a lot of uncertainty about what is seen in the satellite imagery and what it really means. So this is an example of one of the reports from NESDIS during Deepwater Horizon. And you see this kind of line here, and over here it says no imagery available. So that doesn't mean there's no oil over here. It just means they don't know, because nothing was available that was working there. And then you see things getting labeled as possible oil. So again, they're not necessarily sure that they're oil. Usually if you actually read the text carefully, they don't talk about oil, they talk about anomalies in the imagery. So there's something there that's anomalous that looks like perhaps it might be oil, but perhaps it might be something else. And then likewise, even when you have people, trained observers up on a helicopter looking at the water, you know, wow, look at that big oily mess. Well, I think that's actually an algae. There's a lot of natural things out there that look like oil, not only to satellites and airplanes, but when you get down close, they still look a lot like oil. And so there's definitely a lot of uncertainty about exactly what's where out there. Wind forecasts. You guys all have gotten up in the morning and taken a look at the weather forecast to try to plan your day, and you know they don't always get it exactly right. So that's another big piece of uncertainty for us, and that's where we try to quantify that by talking to the forecaster and getting an idea. And they usually have a pretty good idea, actually, about how certain their forecast is. Sometimes they're really very confident, and other times not so much. So we try to capture that. And then the ocean surface currents have exactly the same issues, and sometimes really even more so. The oceanographic modelers are really quite jealous of the meteorological folks because of the meteorological models have this enormous network, at least especially over land, of observations. There's weather sensors everywhere. Not so much out in the ocean. So they're really flying blind a lot more when you're trying to predict the circulation. And so these pictures are a little small, but what this is some work that Bob Weisberg at the University of South Florida did during Deepwater Horizon, where he looked at 5 different models of circulation in the Gulf of Mexico for the same period of time, and he initialized them by this kind of scattering particles in his model where the satellite observations were showing oil, and then watched how that progressed with each of these models. And you can see that these were models that they're all very good models. They have, they're using this sort of enormous amount of computing power. They're injecting information from satellite observations and whatever field stuff is there. But you end up with a pretty different result in the end. There's all the devil's in the details, and they all kind of resolve the details of the physics a little bit differently and give us different results. What we like to say during Deepwater Horizon, of all the models we were looking at, there is no one model that was best all the time, and there was no one model that was best at any given place. So every single day we had to look at all of these and compare how the model was performing compared to what was seen in the field over the last couple of days and make a judgment about which one we thought was performing best at this particular place in this particular time. And we used that for our forecast. But then we'd look at the rest of the models and see what they were showing, and we would use that to kind of bound the uncertainty on our forecast. I will say that it is very, very rare that we've got 5 models to look at for one incident. We're really usually lucky to get one. In which case, it's a little harder to know how uncertain it is. So the ways we can try to reduce some of these uncertainties. Overflight observations are totally key to how we work, and I'm going to highlight this: trained oil observers. That is very, very important. Do we have a section on overflights in this class? Okay, so we're not going to get a chance to talk about how that's done, but the key point that I mentioned briefly is there's a lot of stuff out there that looks like oil, and it's very important that people have been trained and have experience and can help identify, what's a patch of seaweed, what's kelp, what's oil. And in addition to sort of identifying what is oil and what is not oil, also kind of being trained in the common language for how you describe what you see so we know what it means. So that one person's sheen is somebody else's sheen. And what does heavy oil mean? How much oil is that really? So the Coast Guard does training. We do training. Question?
Quick question about that training. So if you had, like for instance, we have an air patrol, and they're available as a resource to go up and fly around and do things. If you were to take a member of our air patrol and train them as an observer, like ballpark, is that like a week-long training and there's a certificate they get, or is it just a 2-hour orientation video like the Weather Watcher thing? Or?
Well, I see Jordan standing up here.
I can take my answer offline too. I don't need to interrupt the whole thing.
No, that's right. It's important stuff. It's key information. We have, we're revamping our curriculum, and we have 3 levels of training. One is like a quick, 1-hour awareness training, just so people understand how we're approaching them. Then we're setting up a aerial observation training for Coast Guard air crews, because they're up there flying around, they're doing all sorts of different missions, and they may be the first ones to come across something. So we want to make sure they're reporting things accurately and objectively, so the people that receive the information know what they're talking about. And then the 3rd level, and that's like about an hour or so training. Because, they're doing these flights all the time. A lot of them have some spill response over flight experience as it is. For responder level training, which I think of as sort of the Coast Guard FOSC types, Federal Unseen Coordinator types, their job is to go out there and not only report what they're seeing, but document it, map it, understand what the implications are of the oceanographic features they're coming across and the different on-water resources. So that's more of like a 4 to 6 hour training, but it's all less than a day. Does that answer your question?
Yeah, I'll have some follow-up for you on that.
Okay.
Thank you.
Yep. Actually, Jordan briefly mentioned another point with overflights is that in addition to observations about the oil, we really appreciate if people can give us some observations about what they see, what's going on with the oceanography. Yesterday I mentioned convergence zones. It's really important for us to know where those are, and they're often quite visible. So that's where overflight map can come back, and it'll map out oil, and I'll have a little convergence. There's a convergence line here, and at this time. And often those come and go with the tides, but if we know what time it was in the tidal cycle and there was a convergence at that point, then we have a pretty good idea that it's going to be there the next day at the same time as the tidal cycle. And then, of course, there's real-time environmental data. So wherever there are observations out there reporting back in real time, we like to take advantage of it. This map is from the state of Texas. The Texas General Land Office funds this program, the TAB system, the Texas Automated Buoy System. And so they've got a bunch of buoys out at these locations that record meteorological information and also actually have current meters on them. So we can go and look and see off the coast of Texas, at least in a few locations, which direction the currents are moving, what's going on with them. So I always really, really appreciate those when we have a spill around there. It's really great to have real-time data. But these kinds of sort of always out there, always reporting back current meters are pretty rare. I think this is actually the only system I know of that's just been active, consistently for years. But at any given moment, there might be some university researcher that's got something out there, and we like to take advantage of it if it's there. So when we put the whole forecast together, there's sort of key elements we have to make sure is there. We try to sort of put it all on one piece of paper. One of the really key factors here is when the forecast was made. So we have to make sure that that is really clear. Up here you have an estimate for. So this is saying, where we think the oil is going to be at noon on the 22nd, but this was prepared at 1900 on the 21st. And so, especially, we may have a forecast that goes out 3 days. Well, 2 days from now, you don't want to be looking at the one that was made 2 days ago. You want to be looking at the one that was made most recently. So when it was made is really important. And then we try to put in the header information what our input data were. If we use models, what models they were. If I looked at data from a wind buoy, which wind buoy I used. Then we have this scale down here, and this is really an interesting thing that we've developed over the years. One thing about oil spills is that different oil spills people scale their own way of thinking and talking to the spill at hand. So what would have been heavy oil during, say, Deepwater Horizon is heavier than anything you'd ever see in a smaller spill. And yet in that smaller spill, people start using, so the heavy oil kind of means the heaviest oil that you'd expect for this particular spill. And not only does it scale with the days, but with each individual spill, but it scales as the spill progresses. So heavy oil or let's say even light oil on day 1 might be heavy oil a week later, if it's the heaviest oil that's still out there. And so what we do is we just have this little picture at the bottom, probably a little hard to see here, that scales that the dark blue in our map here corresponds to sort of what you'd expect to see on the water here. So in this case, the dark blue or heavy oil is sort of, very thick. It's still patchy, but, most of the water covered. And what we're calling light oil here is these sort of spaced out streamers, but still pretty significant. Whereas in some other spill or later on, light oil might be sort of distance really barely elusive stuff. And we actually developed this scale by talking to the people who are doing overflights and saying, all right, so, for this spill this day, what does heavy look like? Where should we put this water? And then there's some discussion. So we always write up a little bit about, what's going on with the physics that's making this happening, what we think the impacts are going to be. And I think, is it on the slide? There we go. And then in the map itself, we have, and we've kind of adapted these blue colors for our best estimate. So this is kind of saying, all right, if all the input data we use, the wind observations, the current models, and all that stuff, were correct, this is where we think the oil would be, and this is where it would be heavier and lighter and all that. But there is uncertainty in all of those inputs. And so we draw this sort of uncertainty bound out around the outside, and that gives you an indication of, where else might the oil be if it's not quite where we think it is. And the way I like to think about this is that you kind of imagine this blob, or sometimes I call it the fried egg. Sometimes it looks a little rounder. And you imagine actually just taking that whole blob and you could move it within this uncertainty bound, push the whole thing north or south or east or west. So it's not so much taking it and spreading it out, but pushing it one way or another. And this bound is really, to some extent, you want to look at the best guess if you're thinking, where am I going to kind of plan to put my skimmers tomorrow? But the bounds are what you want to look at when you want to think in terms of where am I going to go tomorrow to look for oil, to look for shoreline impacts, or, gee, do I need to set up a booming strategy here? All right, it doesn't look like it's going to get hit by the best guess, but it's within the uncertainty bound. So, yeah, you probably do want to protect that beach. So another sort of key factor is who's your audience. And traditionally in oil spills, these forecasts and maps have gone out mostly to the command post and via our scientific support coordinator, or Jordan in this case. And the SSC will then, brief the command on the forecast and talk a little bit about what the uncertainties are and what went into it and what it means and all that. However, in a spill that starts to see a lot of public interest, and particularly in Deepwater Horizon, these trajectories started going out to everyone, everywhere. Other parts of NOAA, other government agencies, the media, the general public. Some people were telling me that you could, go into your local bait store and there'd be a little taped down copy of this trajectory on the counter. So that actually put the burden on us very differently to go, well, people are going to be just looking at this map and not having Jordan there to explain it to them. So that's one reason that I will say that these forecasts for Deepwater Horizon have actually a lot more kind of text and detail on them than our typical ones do, because they were going everywhere and really needed to stand on their own without any explanation. So that was sort of an interesting measure for us, suddenly seeing, stuff we did was going up on the news and unfortunately often kind of misinterpreted. Even within NOAA offices, at one point it turned out that the fisheries folks were thinking about, what fisheries they needed to close, and we're using our forecast to do that, and they were going, all right, anything within the uncertainty bound, we're going to close the fishery. And it's like, well, wait, that's not what it was designed for. And maybe that's not the right way to make that decision. And so we had to make sure that we were sort of talking to everybody who was using these about what it was to be used for. So this is actually one of those examples. So this was at one point during Deepwater Horizon, we had actually sort of two scales of forecast. One was this sort of huge Gulf scale for stuff that might get out into the middle. And then we had a more detailed one for enclosive. But again, this was where basically this entire uncertainty bound is somewhere where there was some chance that you might get a little bit of sheen or a few tar balls out there. And we want people to be aware of that. And perhaps we were flying overflights out from Florida that were coming out and looking around here. But despite the fact that potentially there could have been some oil in there, I don't think that meant you necessarily had to close the fisheries here. If there was any there, it was going to be a really small amount, and it was going to be near the surface. And is that going to affect the bluefin tuna? Probably not. So it was really kind of tricky to communicate both the uncertainty and what it really meant. So a few sort of take-home thoughts about modeling. We like to say that all models are wrong, but some are useful. So you have to kind of just keep that in your head. It's not God's truth, whatever comes out of the model. And also, what you want is a forecast. You don't want just the result of a model. You really need to have somebody that understands what's going on, understands how it's being used, in the loop, sort of putting it all together for you. And no forecast, regardless of how many years I've been doing this, is going to be perfect. And so it's really important to kind of focus on delivering the uncertainties along with us. So key points here: pick the right tool for the job, and to do that you need to know what questions need to be answered, how good the answers need to be, when do you need the answers. And often, in fact, I've talked about the model and I've shown this output from Deepwater Horizon, but our most common trajectory forecast is a one-page written analysis. And especially for something like a fishing boat goes down with 1,000 gallons of diesel or something, really there's only one sentence in that forecast anybody cares about, which is we do not expect shoreline impacts. We can say that, we put that at the beginning, and then we write up a little bit more about why not, what's going on with the currents, what's going on with the winds, how long do we think this slick is going to persist. But really, sometimes you just need that quick little write-up. And then other times you need a lot more complex analysis. And when in doubt, of course, call your SSC. Dr. Jordan. Yes?
You said that that one analysis went out to the public, the media. Why did y'all release that to the public?
There was just an enormous amount of pressure and anything that we didn't release to the public became this big, NOAA's keeping secrets. The Coast Guard is in the pocket of BP and not telling us what's going on. So it wasn't really my decision, but it was, when there's that much public pressure, it was really important to just be as open as possible. And also, a lot of people had good reason to want to know what the forecasts were. We actually literally got a call. I don't know how they got the phone number, but we got a call on an emergency line trying to find out whether somebody should, cancel their wedding on Miami Beach due to the Deepwater Horizon. So, that was kind of an extreme example, but a lot of people did want to know, and they have a right to know.
But I guess my follow-up is it's kind of like going to the doctor's office and they give you your lab, but if you don't know what they do,
yes,
then you're left to speculate and guess too. So
right.
I kind of equate that.
No, actually, in fact, it's exactly like that, and that's why a lot of labs won't actually give you the lab results directly before you had a chance to get it presented by your doctor. So we much prefer that this stuff is presented by someone like Jordan to its target audience, but sometimes that's just not possible. And there's a lot of public interest. But what we do instead is put a lot of stuff on there to try to explain what it means as much as possible. Are there any other questions before I move on? Yeah?
So do you get an opportunity, like in situations like Deepwater Horizon, you guys actually know you're forecasting for 24, 48, 72 hours ahead, so you're staying ahead of it. Do you get an opportunity to go back and look at the correctness of the forecast and how it actually worked out?
Well, actually, I guess somewhere it wasn't on the sort of bullet point in the slide, but one of the key steps actually when we do this every day is we get our observations, and then we do actually compare to what our forecasts have been over the last couple days, so we can adjust what's going on. That's actually a big step. We like to say we reserve the light to be smarter later. And the forecasts get better. The very first one, there's uncertainty in everything in the first one in terms of actually what got spilled and how much and where is very uncertain, as well as what's going on with the winds and currents and all that. So we do always, look back in a kind of on process. We generally don't have the time to kind of go back and do a sort of it'd be nice to do like a thorough analysis of sort of like all of the whole Deepwater Horizon principle and what worked every day. But we do definitely every given day look at what's been going on and how was our forecast yesterday, and if it was off by a significant amount, try to figure out why so we can adjust in the future. Any other questions? How much time?
So in light of your last comment, when you're not working on an incident, do you use all of the data you guys collected for Deepwater to refine the operational models, or are they just what's your sort of model evolution of that?
Yeah, we do actually. What I'm mostly spending my time on now, when there isn't an active incident, in fact, is developing the next version of GNOME. So we develop these tools in-house. And that's exactly what we do, is we use our experience and sort of what the limitations were in the model to try to improve it in the future. So I want to flip through quickly. I'm going to just really quickly demo GNOME, demo ADIOS. I think in the printed version this URL is wrong. It says GNOME again, so hopefully you can figure that out. If you get anywhere on our website, you'll be able to find it. And I also want to briefly mention a tool. I'm not going to get to demo because I forgot to put it on this computer, but this is a little thing I wrote called the NOAA unit converter for oil spills. So as we mentioned yesterday, we're dealing with like API gravity, and there's some weird units we use in the oil spill biz. And what I found is that there's a million unit converters out on the internet and that you can download. But any of those unit converters that have the weird units we need have everybody else's weird units, and it's really hard to use. So this has all the stuff you'd want for an oil spill and not much else. And this one, actually in particular, it has a little oil quantity calculator. So in the US, we usually deal with oil in terms of volume, barrels or gallons. But in Europe, they talk about oil in terms of metric tons. So if you actually want to convert a metric ton of oil to how many barrels it is, you have to not just know that it's oil, but have to know what actually the density of that oil is, whether it's a heavier oil or a lighter oil. So this is one of the little extra features for oils that's kind of handy, is that you can put in either I've got a kind of set of generic oils you can pick from, or you can specifically put in the density, and you can do that in any units you want, API degrees or specific gravity or any of those. And then it'll convert from mass to volume for you, or vice versa. So that's kind of nice. There's also a little latitude, longitude thing here that'll convert from decimal degrees to degrees, minutes, seconds, and vice versa, which we have to do a lot, and it's sort of handy to just have it. So this is downloadable from our website as well. And now let's try to quickly whip up. I've got 10 minutes? Yeah. So Judd warned us against live demos, but I'm going to try it anyway. And we'll see how it goes. So when you download GNOME from our website, you can install it, and then you also can get various location files. So if you start it up, it gives you this little splash screen. And then it just gives you a little warning about what should you use it for, what should you not use it for. And if you click in case of a spill, it basically tells you to call Jordan. But you basically kind of bop through this little wizard, and the first thing you do is actually select your location file. So I'm going to do Santa Barbara. Well, actually, I'm going to do San Diego Bay because it's fairly simple. And you get a little welcome, and it tells you what you need to do. And there's actually the various references we use to develop it are there if you want them. But the key information is, when you want the model to start. It starts out with, now. And I talked about uncertainty. So right here, one of the options is include the minimum regret or uncertainty solution. I'm going to turn that on because I think you always should. And I'm also going to turn on show currents. You can turn these on and off later as well. And then for winds, you can either just give one wind constant over time, or you can put in a whole time series of wind if you have a forecast that's going out. And I'm going to just do constant now because it's a little quicker and easier. And you can actually just either click on the little compass rose here or type it in. And I can either put in cardinal directions, east, southeast, whatever, or you can also just put in degrees true. And the thing to always remember about wind is it gets reported the direction it's blowing from, not the direction it's going to. So if we have a wind from 45 degrees, that's the northeast. So oil's going to move to the southwest as a result of that. A little information about what's here. And then you've got your model. I'm going to zoom in a little bit here. So here's San Diego. I had currents turned on, so you can see the tidal currents going here. Right now it looks like we're in the middle of, at this particular time, which is, today at 0800, looks like we're in a pretty good ebb current. If I don't do anything else and just press play now, what you see is how the currents are changing over time. So San Diego is primarily tidally driven, so it's just going in and out like you'd expect. But then you might want to have a spill. I'm going to get in a little closer. So this little leaking ship tool lets you put in spills, and you can click on one point, or you can also drag, and you might even say have a ship was leaking as it moved. So you get that whole line. So now the start and stop position that I just clicked on show up here, and you have a start. And this is all happening at the start time, and you could change that to whatever you want it to be. And what I'm actually going to do is have it, say, leak over maybe even just an hour in this case. Well, 2 hours. So it starts at 0800 and goes to 1000. And it says, you didn't say how much oil got released. You got to do that. So I'm going to do that. 100 barrels. So I'll tell you a little hint that I mentioned yesterday that kind of where the oil goes isn't really a function of how much gets spilled. It's pretty much the same physics regardless. So regardless of what I put in here, we're still going to see 1,000 little dots moving around, and they're going to move the same way regardless. But in the end, if you want to do some weathering, what the heck, I'm going to make it a diesel fuel so I can show you that. Now the quantity starts to make a bit of a difference. Ooh, so big mess. And then once you run it, you can actually go drag back and forward with time. I'm actually going to turn off the currents for a second so we can kind of see what happened. So this is all pretty quick. So what we have here is the ebb tide pushing it out, and also here's my northeast wind. So it's tending to push it that way. And so what we're going to see is this shoreline affected a lot more than the other one because of that easterly component of the wind. And you can see what gets stuck on the shoreline. And it actually when it hits the beach, it gets stuck there, and then we have a little algorithm that some of it refloats, because that's what really happens, and that can be adjusted to some extent. But so that's just the quick basics. There you go. You can make new spills, and we kind of call it the oil spill video game sometimes.
So in the shape file, the tides are automatically inputted for each location?
Right. So the location file, if it's a tidally dominated area, will have the tides already in it, ready to go. All right. Since I've got very little time, I'm going to really quickly show you ADIOS. And again, you can just go to our website, download this, and there's a lot of good documentation. So ADIOS is what we call kind of non-location specific. It doesn't care where you are. It just cares what the conditions are at the time. And so we have kind of little quick instructions. This is what you need to do in order to model how oil is going to weather. You need to know what kind of oil it is. You need to know what the wind and wave conditions are. You need to know what the water conditions are. And then you need to know how much got released and at what rate. So when you click oil, what you get is we have a big database of all the oils that we could find that we have data for. So there's a huge list in here. The amazing thing is, despite this huge list, chances are the one that got spilled is not in this list. There are so many, and this is a combine of crude oil products and refined products. The refined products are particularly tricky. I'm going to hit a D, which will get me close to the diesels. So we have a few diesels in here. One issue is that in Alaska and Canada, it gets very cold, so the diesel fuels have to make sure they don't have waxy components in them that'll freeze up and clog fuel lines. So you notice those are actually a little bit higher API, 38.8, 39, and these, I'm going to see if you can see that. These are diesel fuel, Southern USA. So in general, I'll at least kind of just choose between that. Am I in a cold climate or a warm climate? And I'll pick one of those. The details are quite different. The general trend is not. I'm going to see if I can find, say, there's Alaska North Slope crude here. There you go. Notice even that there's a whole bunch of different Alaska North Slope crudes. And their APIs vary from 26 to 27. So if I don't find exactly what I'm looking for in here, what I'll try to do is find something that is from a similar region and similar API. And, you know, you hope you get close. You also actually can, if you can get detailed chemistry information on your particular oil, you can put that in here. I'm not going to show that because I think I just got like the 2-minute warning. So that's the oil. Wind and waves, as we talked about a little bit, weathering is affected by the wind speed, and the dispersion especially is affected by the wave conditions. So you need to know that. I'm going to make this go away fast. You can pick your units. So 15 knot wind. Direction actually doesn't matter unless you also have a current that's in a different direction. And then I'm going to compute the wave height from the wind. That assumes unlimited fetch. What you also can do is put in a fetch. If you know that you're only a mile from shore in the direction the wind's blowing from, you might want to put in a 1 mile fetch and the waves will be a little smaller. You can also just put in a known wave height if you have that. Okay, so for water, water temperature is really important. For the most part, the oil is a thin film floating on the surface, so the temperature of the oil ends up being the same as the temperature of the water, and the temperature of the oil varies how quickly things evaporate hugely. So we have a couple examples, and often you can actually go out to National Data Buoy Center, and some of those offshore buoys have temperature on them, and you can know what temperature the water really is right there. Otherwise, you can estimate. Anyone know what the water temperature is like, say, in San Francisco Bay this time of year? 53 or 55. See, there's some uncertainty, but not much. Salinity and the water sediment load actually affect the sedimentation process, how oil sticks to sediment. So I'm going to leave those as a default, and I'm not going to put any current for now because I've got 1 minute left. Release. Okay, let's make it easy. You can do an instant release all at once. You can have it come out over a couple of hours, and we have a way to calculate, actually, if you have a tank of a given size with a hole of given size, how quickly it will release. And I'm just going to dump 1,000 barrels right away. Now, right away isn't actually right away. I think the minimum amount of time it'll do is at least 10 minutes or so. And then you solve. And what pops up is our kind of general plot of the oil budget, where it's gone. So this blue section is what's evaporated. Now remember, this is a crude oil. So in the beginning, it evaporates really quickly, and it kind of tails off somewhere. This is out of 1,000 barrels, so this is something like almost 40% ends up evaporating after a few days. Moderate amount disperses. So, and you can also look at a lot of sort of individual outputs there. The one I look at most is the oil budget table, which is basically the same information we just saw in that graph, but in tabular form. And often I'll copy and paste this and stick it into our trajectory report. So this tells you so many hours into the spill, how much has been released by then. In this case, it all got released at once, but it could have come out. And how much is evaporated, dispersed. And often this remaining number is the one we really care about. How much is still left out there? So in the case of a crude, about a little more than half of it is still left 5 days later. And that's going to pretty much hold steady. Once the light stuff is gone, that's really about it. The 120 days is the longest period that we'll even run the model, because there are longer-term processes that start to kick in, more biodegradation, photooxidation, and we're not modeling that here, so we're not trying to make a prediction of what the oil is going to be like 2 months from now. We're really just focused on the first few days. And I think I'm out of time. So I'm sorry, we didn't have more time to run through this, but you've seen it a little bit. I encourage you to go to our website, download it, play with it. Don't put it on your Coast Guard workstation because you're not allowed to, but other than that, you're free to roll.